Thank you, Andrew, for recording the slides. Makes it much easier. My name is Daniel, and I would like to give you an update on our project, which is called Earth in Other Solar Systems, which we call EOS. And you probably remember, or most of you do, that EOS is one of the large teams within NExSS. Our goal is to understand how do habitable zone Earth-sized planets form and how do they acquire their volatiles and organics, which are critical for life. That basically allows us to identify which systems are more likely to have habitable planets than others and understand what factors influence their formation. So I'm the principal investigator of the team, and we have the deputy PI, Tom Zega, here in the room. We have three teams, teams 1, 2, and 3. Led by Lucy Zuris, Ilaria Pascucci, and Fred Chesla. Lucy will be here tomorrow. The team itself is rather large. We have about 25 faculty senior investigators and about 15 students and postdocs joining the team. The lead institution is the University of Arizona, and we have involvement from a number of other institutions. So our approach to this ambitious and large question is interdisciplinary from the beginning. So we are combining astronomical observations of physical and chemical properties of prestellar cores, comets, disks, and exoplanets to study the continuity of the physics and chemistry through these stages. We also carry out state-of-the-art laboratory analysis of meteorites that serve as time capsules, preserving conditions and composition from the early solar system. We also combine these with first principle-based fundamental calculations to explore some processes, especially freeze-out of organics and volatile molecules to grain surfaces that haven't been done to the level that's needed. In addition, we are carrying out and further improving state-of-the-art simulations for disk evolution, both physical and chemical perspective, and also for planet formation. So these kind of techniques all produce new knowledge. They all produce papers, and I will show you a list of papers we have published in the first year. But the real benefit, something that's only a Nexus-like coordination allows us, is to integrate this research together. And all the pieces we are carrying out as state-of-the-art, but these connections just haven't been made at the level before them. And it allows us to be much more ambitious in addressing our goals. So we combine basically these studies, the observational studies and laboratory studies with the models. The models drives the questions that the observations try to answer, and then feed back to constrain the models and verify them. So the products of the investigation, in addition to the knowledge and generated, is a predictive and diagnostic model for planet formation that's very ambitious and more comprehensive than anything existed before, as well as the Genesis database, which will contain more than 1,000 simulated planetary systems, complete with their formation history, abundances, physical and chemical properties. Through many places in this framework, we can and we are connecting to other Nexus teams that help us to complete the picture, the studies we are doing, and provide us information to refine our assumptions and verify our results. So science-wise, we divided our projects into 3 teams. I mentioned teams 1, 2, and 3. The first team is exploring the history of organics and volatiles in the solar system. The second team is exploring how organics and volatiles are processed once they are delivered into protoplanetary disks. And the third team explores how then these processed organics and volatiles then delivered to forming planets. Together with Nexus, we will use this knowledge, this actionable knowledge, to characterize nearby planetary systems and identify which are more suitable for example, biosignature searches. A bit more detail can be found in this flowchart, and I have a large number of projects to cover. So I did want to point out that we put together a little booklet that was mailed out. We have also hard copies here. Please take one if you like. I will not try to tell you everything we have done in the past year, but just to give you a high-level overview. So in team 1, we are combining radio observations, molecular surveys of chemistry, organic chemistry and complex chemistry in pre-stellar stages, with detailed studies, state-of-the-art studies of meteorites, carbonaceous chondritic meteorites, and together these studies, laboratory work, and astronomical observations provide us with a starting inventory of organics and volatiles in the solar system, which we take as a template. These are, if you like, our initial conditions for a physical-chemical model. In team 2, we are surveying the evolution of protoplanetary disks, both physical and chemical, from physical and chemical perspectives, exploring how the disk structure changes, what are the effects of photoevaporation, for example, internal and external, how the chemistry in the disk is changing. These are providing our boundary conditions for the physical-chemical model. In project 2.4, we are putting the initial conditions, the boundary conditions together, and to constrain an integrated physical-chemical model for disk evolution that can tell us what is the composition as a function of time and location in the disk, and as a function of stellar properties. These then provide input parameters for planet formation models. In team 3, we are exploring how organics and volatiles are delivered to the forming planets and how the planets themselves form. This includes very large, very ambitious embodied simulations in which we are forming more than 1,000 planetary systems and keep track of where they accreted material from. And we will explore the planet formation and its outcome as a function of the initial conditions, changes in the disks, and we'll use our observational studies to set the initial conditions right. We will, and we are iteratively comparing the predictions from these embodied simulations to state-of-the-art databases of exoplanetary systems, in part derived from the Kepler Database, and also to observations of specific systems, transiting planets, where we can learn a bit, quite a bit more about the composition and properties of the planets themselves. So a direct product will be of this process is the Genesis database that will be available to the entire community, but earlier versions will be made available to the NExSS community too. So I just wanted to speak a little bit more about what we have done in the first year, what are our results, and how we collaborated with other teams. So our team is large, and we had many projects that were ongoing, and many more have been started over the past years. This is actually an incomplete list of refereed publications that have drawn from our expertise or were entirely motivated by the EOS work and enabled by that. Several of these were represented in various press releases and the media, so you may have seen them. I will show some examples. I wanted to highlight 3 papers. These are papers in which multiple NExSS groups have co-authored jointly with us. This other blue frame shows papers on which we have posters, and we have EOS members here in the room and will be here today and tomorrow, and I urge you to speak with them. So I wanted to borrow Andrew's conceptual map to illustrate the connections we have already made within NExSS. So we are close to the center. A stands for Arizona, and these are the teams with which we have co-written papers in year 1, and these are the teams with which we have worked in different other ways, whether organizing events, writing reports, visiting, giving seminars, etc. This is a list of some of the collaborative efforts that we have carried out. I will not go through all of these. I just wanted to point out a few of them. So we have, together with the ASU team, with Steve Dash's team, we have co-organized the Winter School, which was held at the University of Arizona's Biosphere 2 station, and we have hosted over 30 students and postdocs from NExSS teams and also from the broader community. It was a real fun event. We are also leading a SEG 15 study. I'm chairing that. That's exploring science questions from direct imaging missions, and that's also something that many NExSS teams are participating in. I will not go into the details, but we have seen NExSS as a great opportunity, and we are making good use of it. I wanted to show you just some highlights, and we have posters out there with many EOS members here, so I hope you will take the opportunity to chat with us in the next days. We have projects using high contrast imaging in which we are exploring properties of debris disks. This one is in of particular interest. Beta Pictor is a disk seen at John. It's a disk in which we have previously discovered via direct imaging a short period, relatively short period, direct image planet. We can watch this giant super Jupiter orbiting in the inner disk. And with this new HST data that's very sensitive, very accurate, and we can probe changes in the disk over 15 years. We are also carrying out a large extreme AO survey, about 100 young stars, where we are searching for planets, determining the occurrence rates of giant planets. And along the way, we might make some unexpected discoveries. This is a study that was led by Kevin Wagner, a first-year graduate student in Arizona, who discovered this spectacular two-armed spiral arm in a disk, young protoplanetary disk. High Smulders, who's in the room, has led studies using the Kepler database, determining occurrence rates using complete data sets and correcting for various effects. One interesting result he found, that was also in the press, was that if you break planet occurrence rates, you determine them by spectral type. Not only there is a difference between M dwarfs and all the other types of stars, but in fact there is a spectral type dependent planet occurrence rate. And both in the frequency of planets and also in their location, which tells us that planet formation is stellar mass dependent. Heiss in another paper also found that not only the M dwarf planets are more numerous, but in fact they contain more solid mass than planets around more massive stars, which is a very exciting result. We are also carrying out a large transmission spectroscopy survey in which we are using the 6.5 meter Magellan telescope and soon the MMT in the north. We have already observed 30 transits in which we are able to survey and basically observe the optical spectrum with most of the optical spectrum with a single shot. This is a result from Ben Rackham, who is in the room too. He has a poster on this. This is a super-Earth transmission spectrum obtained at the highest accuracy and with most data in the optical. This is a capability that we'll be able to utilize for follow-up test targets. And I wanted to end by pointing out our website. We have put together a website which we also use as a way to communicate our results and our plans to the broader exoplanet community and also to the Nexus community. And I urge you to get a copy of our booklet if you are interested in learning more. Speak with our members who are here and check out the posters, and speak with us if you think that we can connect, because I'm sure that there are many other connections we can explore. And I wanted to stop there and thank you.
Okay, questions for Daniel?
Hi, Daniel. Bill Moore, Living Breathing Planet team. I understand meteorites are what we have, but they're not, well, primitive, they're not unprocessed. Are you at all concerned that using them as the basis for understanding the bioavailable and biocritical components may bias your outcome towards, based on processes that are unique to our solar system and what happened in this particular environment?
Okay, that's a very good question, Bill. So there are really two aspects. One question is the solar system typical? And whatever we learn from the solar system, can we take that as a template for all the other planetary systems? The other part of the question is how can we account for any processing that happens in the parent bodies? And these are not new questions, neither of the two. For the first one, there's just so much we can learn from the solar system that it would be silly not to include that. At the same time, we have to keep in mind that the solar system may in some way be different from other planetary systems. The observations we do here, we are comparing them also to what we are learning from disk processing and disk studies in Team 2, where we are observing several hundreds of disks with ALMA and also infrared spectroscopy. We are assessing also dust processing there. If we find that we have evidence that the solar system was very different, we'll be very happy because it will be a very exciting result, even though if it limits to some level the how much we can use the information from there. The answer to your second question is also related. What our focus is not simply just to take an inventory of what is in meteorites and accept that as an initial condition, but it really is to understand what processes have played a part in shaping that distribution. We can actually map grains and identify grains at very high spatial resolution that are pre-solar grains and study those and study mineralogical context for the grains that we are exploring. So I think that we thought about both of these. They are both interesting questions, but they can be considered.
Other questions for Daniel? Okay, if not, let's.
Thank you.